We will now give a definition of an integral in 2 dimensions. We will only give the definition of a 2-dimensional integral over a rectangle. In the general setup, we have a function f of xy and a rectangle AB times CD. To define the integral of a function over a rectangle, we will begin by defining a Riemann sum. Now, before getting started, let me just mention that in the previous examples, f was the graph of a function, or it was the weight density function. Either one works. F could be either one or anything else. So it doesn't matter what the physical interpretation of f is. The same procedure that we're going to do here works for any interpretation of f. Okay, so the rectangle, x goes from A to B, so let me label that. Y goes from C to D. And next, we're going to pick sample points in each subrectangle. Now, it doesn't matter what sample points that we pick, just as long as we pick exactly one sample point from each subrectangle. So in particular, we don't have to pick the midpoints, though we can certainly pick the midpoints. That allows us to make better formulas or closed forms for formulas, but we're not actually going to be computing Riemann sums in this class, so we don't really care about that. We just need to pick any point in the rectangle. And now the width of each one of these, in the x direction, we're going to call delta x. We're going to say that it's constant width. And in the y direction, we're going to call this delta y. So the Riemann sum is going to be, at each one of these subrectangles, we're going to multiply the area of the base times f evaluated at the sample point. So to do this, since I tell you that I want one Riemann sum, we're going to label each one of these rectangles. So for example, this could be rectangle 1, this could be rectangle 2, this could be rectangle 3, and so on. So in this particular example, we have 24 rectangles. And we're just going to say that the xy coordinate at each sample point, we're just going to call it x4, y4, or x5, y5, x6, y6, so on and so forth. So we're just going to label the coordinates based on the numbering of the rectangle. So then the Riemann sum is going to be the sum from k equals 1 to 24 of f evaluated at the sample point times the area of each subrectangle. And we know that for this particular problem, the area of each subrectangle is just equal to delta x times delta y. And so really it doesn't depend on k at all, and so we can get rid of this k. So this is the Riemann sum for this integral. As you are probably expecting, the integral of the function over this region is going to be defined as the limit of these Riemann sums as delta A goes to 0. And that's what we have here. Let f of xy be a continuous function defined on this rectangle. Then the integral of f over r is defined as the following limit. It's the limit as delta A goes to 0 of the sum k equals 1 to n f evaluated at a sample point xk, yk in the kth interval, or the kth subrectangle, times delta A. Now, let me just mention that you might remember from Calc 1, there was a certain notational convention that was used. Whenever we were just taking any sample point and we didn't care about whether it was a left endpoint, the right endpoint, midpoint, we just wrote a star, and we can do something similar here. That just indicates that we don't actually care whether it's the left endpoint or right endpoint, it's just any point in the subrectangle. And I'm going to use that notation here. So here, xk star yk star is just any point in the kth subrectangle. And of course, if the area of the rectangles is going to 0, then we need more and more rectangles. So this also means n is going to infinity. So this is somehow inconsistent notation, but I think you understand what it means, especially if you think back to analogy with Calc 1. Now let me just mention that here in the definition, we use two integral signs to denote the fact that this is a two-dimensional integral. But it would be just as fine to write this with one integral sign, just as long as we remember that we are doing a two-dimensional integral. Now, in the next video, we're going to learn how to actually compute a double integral. And we're going to use the iterated integrals that we saw in the previous video, or in the previous lecture.